morning, everyone. I am Hamada Elshaboury from Politecnico di Milano. So, over project life cycle, a vast amount of documents related to design defects are generated. However, learning from this defect is not promoted as a practice in our construction sector, and also these documents are shared as paper-based documents. So, which means it requires effort times to elicit knowledge from these documents. And moreover, most existing information about design quality issues is based on opinions. While this information provides good indicators, but it's often biased, provide low level of details, making it difficult to make reasonable improvement. So we propose a methodology based on LLMs and prompt engineering to process one of these documents. Interesting one, design inspection reports. Design inspection reports are a rich source of the design defect text containing a list of design nonconformity lists and produced during the validation phases before tendering, for example, in Italy from 1994. So our objective is to process these reports to extract and standardize information from these reports, store it in a database to apply statistical analysis to measure design defects indicators, analyze defects distribution across design documents, building a system in space, exploring inconsistencies relationship between design documents and the relation between defects and project metadata, and also to share this information with designers to avoid these defects, and with inspection bodies to improve their verification actions, and the contractors to write claims about the design. So we started by asking which information could be extracted from each design defects, how to be standardized, which AI model should be used to automate the process, and how to be implemented, and also how to be evaluated, and finally which knowledge could be elicited from these defects and how to make this information accessible. So we developed these main steps, and for today, this is our scope for our presentation today. So from each design defect text, we can extract the name of the document checked by inspector, the object related to the defect itself, and the reference document, which the checked document is inconsistent with it. So to formulate this, from each design defect text, we extract the checked document, where the defect is identified, the reference document, the described defect, and the related object. And then we classify all of them into specific categories. For information extraction, we pre-process each inspection reports to prepare the list of design defects, provide this for LLM with some view shots and our prompt to extract the predefined information entities. Then we evaluate the results. So if the results are okay, we validate the prompt and the LLM. If not okay, we can use another LLM model, or also to apply error analysis to improve our prompt and to increase the number of shots. For pre-processing, we remove non-textual parts from each inspection report, divide complex cases, and remove any sensitive data, and remove any duplicated design defect text by embedding the text and to measure similarity between them. Our prompt consists of two parts. The first part is the system message. This informs LLMs about its task and also knowledge areas. The second part informs LLM about information to be extracted and the extraction rules and any general notes. For executions, we developed two functions. The first functions prepare LLM message by adding system message, instructions, few short examples, text to be proceeded, and finally to send this to LLM and to receive the response from LLM. The second function passes each defect text from our list to the function one, and to receive the response and to parse this response and to extract the response from the response of LLM and to store it in a results list in a JSON format. For experiments, 200 76 design defect texts were collected to prepare our ground truth. 15 cases were selected based on defect types for few shot scenarios, and the others 261 were used as a testing data set. We tested 3 LLM models, GPT-4, Mistral, and Llama 3, and we used four few shot scenarios, 0, 5, 10, and 15 shots. And we evaluated the performance of the models from 3 perspectives: performance, computational cost, computational time. For the performance, we used exact match, which is a binary metric, 0 or 1. Blue, rouge, N, they are n-gram metrics measuring the overlapping, n-grams overlapping between the generated text and ground truth text. Blue focus on precision, and the rouge N focus on our calculate F1 score. BERT score and the SBERT, they are semantic similarity metrics using embedding to measure similarity between texts. BERT score works at token level, while SBERT works at sentence level. For the results overall, as we see, GPT-4 achieved the highest performance between all evaluation metrics and also view shot configurations. And also, as we see, the performance of the models improved as the number of few shots increased. For metrics, exact match yielded the lowest scores, indicating that achieving word-to-word matching between the generated texts and ground truth text was challenging. For n-grams metrics, scored higher than the exact match but less than semantic similarity metrics, indicating that models were able to capture some overlapping words, but not identical matching between generated and ground truth text. Focus on H1, H information entity. For the checked document, models were able to achieve a good performance. And also, as we see, maybe 10 or 15 shots is the suitable number to extract this entity. And also for the reference document, model achieved a good performance, but less than the performance for the checked document. And for the object, GPT-4 and Mistral, both of them followed the similar performance trend. And according to rouge N, for example, the performance of GPT-4 was about 0.75 at 15 shots. For the defect, as we see, the 3 models also followed the same performance trend. But for example, according to SBERT metrics, the performance of the model was about 0.8 at 15 shots. But as we see, exact match, blue, and rouge N metrics are not suitable to evaluate LLM performance for our task to extract this information entity. And also to extract the object, exact match and blue are not suitable to evaluate LLM performance. For the cost, Llama had the highest number of tokens, input and output tokens, and also the cost, while GPT-4 has the lowest input and output tokens, but came second before Mistral due to its high cost rate. For time, as we see, Mistral had a balance performance, achieved a good balance between performance, stability, and efficiency, followed by GPT-4. As a conclusion, we developed a methodology for the performance. GPT-4 ranked first, and Huawei ranked second in computational cost and time. Exact match n-grams is not suitable to evaluate LLM performance to extract defect. Exact match is not suitable to evaluate object extraction. There were some formatting errors in LLM response to extract text contained multiple document names, object, and defect, so we need to add more explicit instructions to our prompt. There were also extraction errors for defect and object, specifically in complex cases, so we need to increase the number of shots, but it means the cost, so we will use RAG to solve this problem. And for our future work, we will implement the previous recommendations and comparing the results. Also apply information classification step, performing statistical analysis, and developing the information retrieval system. Thank you for your attention.